So lesson number 2 just looks at relationships between quantities. So in math, we generally are always looking for patterns and relationship. We learn how to multiply through patterns and through relationships. We recognize that multiplication was just a different form or a quicker form of addition. So when we're looking at patterns and relationships between data, then we've got our relationship between our two quantities, such as the value of a computer compared to its age. The older the computer is, the less it's worth. Or the price of a watermelon related to the weight. The heavier the watermelon is, the more money it's going to cost you at the till. The time taken for a person to walk to school is related to the distance to be walked. The further you are away from school, the longer it's probably going to take you to walk. So in mathematics, a comparison between two sets of elements is called a relation. So give me another mathematical type relationship that exists.
How do you do this?
So I gave you 3.
How much your groceries will cost relative to how many things you buy.
Okay. This would help if I spelled groceries right. I could have the amount of money you make depends on the number of hours you work. Or the distance that you travel depends on the speed that you're traveling. Okay? So when we are representing relationships, there's 7 different ways. There are different ways that we can express this relationship. And some of them you're already familiar with. In words. This is an example of expressing the relationship in words. So yesterday when we were looking at the toothpicks and the triangles, we said that the number of toothpicks is double the number of triangles increased by 1. That's describing the relationship in words. A table of values. So we had those charts yesterday that we had the number of triangles, 1, 2, 3, 4, 5 triangles, and the number of toothpicks, 3, 5, 7, 9, 11. A set of ordered pairs. Well, we took the numbers from the table of values and we created a set of ordered pairs from it. So we had 1 and 3, 2 and 5, 3 and 7. Mapping or an arrow diagram, which is a new one. We haven't really seen that one yet. An equation. So going back to that toothpick example, we said that the number of toothpicks P was equal to 2 times T plus 1. A graph, we graphed that relation. We put the points on the graph. We didn't join them. And then function notation, which we'll look at the latter part of the chapter. So if we look at the following relation, the cost, C, in cents per kilometer of driving a car is related to the speed, S, in kilometers per hour at which it is driven. Because there is kind of a plateau. So if you drive your vehicle really, really slow, it's not actually going to be cost effective. And if you drive your car really, really fast, it's not cost effective. So there is a balance. There is a speed at which your car is traveling at the most effective cost measure. So the example illustrates a relation between two variables, the cost and the speed. In the statement of the relation, the cost is dependent on the speed. And yesterday we talked about input-output. The cost would be the dependent variable because it depends on the speed. The speed is the independent variable because I control the independent variable. I control how fast I'm going in the vehicle. When representing the relationship, we can think of independent variables as our input and dependent variables as the output. So before we consider how to represent this relation, we need some data. We need to know what some of our input and our output values are. The other thing too is input values make up the domain and output make up the range. And in lesson number 5, we'll focus more on what domain and range is. So obviously we would not attempt to find out the cost for every possible input, every possible speed. So we might just choose certain speeds and then be able to graph in between. So 10, 30, 40, up to 120 kilometers. So here's my table of values. At 20 kilometers per hour, it costs me 10 cents per liter. Or sorry, 10 cents per kilometer. Yes. At 120 kilometers an hour, it is also costing me 10 cents per kilometer to drive. But right here, I've got at 70 kilometers per hour, it's costing me 7.5 cents per kilometer for cost and speed. So this represents my table of values, which I then turn into my ordered pairs. My inputs were my x variables, or they go horizontally. My outputs were my vertical values. And then we have our graph. So we've drawn a set of points together that make this nice curve. Could I join the points of this curve? Is the data continuous?
Yes.
Yeah. The only thing that limits me is the measuring tool for my speed. But is it possible to drive between 60 and 80 or 60 and 70 kilometers per hour? Yes. This is my mapping diagram. So what do you notice about the first bubble? It's my inputs. And what's the second bubble? And then what do I have in between?
Arrows.
Arrows. And the arrows are going to the right output. So 120 goes to 10, and 20 is also mapping to 10. 30 maps itself to 9.1, and 110 maps itself to 9.1. Okay. Now the next page, again, it talks about the fact that it's obvious that an output value could have been determined for every input value greater than 0 up to the maximum speed of the car, which means I could join the data. And if I join these points, I could then develop an equation, which you're not expected to do at this point for this type of graph, but we could develop an equation that would give me the relationship for any input value. So if I wanted to know what the cost would be if I traveled 106 kilometers per hour, I could use this equation to find that out for me. Now, this particular equation is only going to be valid for a certain amount of S values. In other words, it would not make sense to put S is equal to 5,000 because I can't travel 5,000 kilometers per hour in a car. It's not going to work out very well for anyone involved. So there's a limit as to the possible inputs that I would have in this scenario. But if I didn't have a particular situation that this equation is surrounded by, my S value could be anything that I wanted it to be. It could even be negative. Again, in this scenario, I wouldn't have negative speeds. Going backwards is not a negative speed. Okay? So again, because the data is continuous, I can join these points in a smooth, we make it a smooth curve because we can see from the points that it is making this U shape. So I would join my points in that U shape. Independent and dependent variables in a relation. So when we're talking about independent variables, my inputs, in an ordered pair, the input is the first coordinate. In a table of values, the input is usually given first. In a mapping diagram, my input was the first bubble, and I mapped to the output. In a graph, the input, that independent variable, is along the horizontal axis. And in an equation, the input is usually, actually it's better to think of output. In an equation, we isolate the output. We solve for the output because we put in the input. Okay? So those independent variables in a table of values is the first column, the first coordinate of an ordered pair. It's the first bubble in my mapping diagram. It's the horizontal axis. And in an equation, it's the part that's with all of the other stuff. The dependent variable in my ordered pair is the second value. In my table of values, it's the second column. Or if it's a horizontal table, it's usually the bottom row. In a mapping diagram, the arrow points to the dependent variable. It's that second bubble. In a graph, the dependent variable is my vertical axis. And in an equation, it's what I've isolated. So if we look straight, jump into class example number 2. The diagrams show relationships in different ways. In each case, we're going to state the independent, the dependent, the input, and the outputs. So I'm going to do A with you, and then I'm going to have you do B and C on your own. So in A, what is the independent variable?
P.
How do I know it's P?
Because the arrows are coming from those numbers.
Okay, so then the dependent variable would be Q, because the arrows are going to Q. What are the inputs? And what are the outputs? 10 and 16. So I want you to do the same for B and C. For B, what is my input? B is my input. What is, sorry, that would be my independent variable. What's my dependent variable? A. What are my inputs? And what are my outputs?
15, 12, 15.
Okay, do I need the 15 twice? No, so I could just put 12 and 15. Okay, so if I look at C, what is my independent variable? B. What is my dependent variable? What are my inputs? Okay, and what are my outputs? Okay. So now in class example number 3, what is my dependent variable in A? So what's my input in A? R. Is pi an input? No, what's pi? It's a number, it's a constant. So it's a symbol, but it represents a constant amount. So what's my dependent variable? C. Okay, so in B, what's the independent variable? T. And the dependent? H. And then the amount of sap obtained from a maple tree is dependent on the time that the container is left on the tree. So what is my independent variable? Pardon? T, the time. And my dependent would be S, the amount of sap. Because the amount of sap that I collect depends on the amount of time that I've left it there. So I want you to do questions 1, 2, and 3. So what we're going to look at now is looking at relations that are defined by an equation so that we can sketch a graph by plotting ordered pairs. So when you're given an equation, what you would do is you would make a table of inputs. So you would choose appropriate input values. And depending on the context of the question, we can talk about how you would choose those. then what you do is for each of the input, you would calculate the corresponding output. Once you have your table of values done, you get to plot them on the Cartesian plane. So if we look at the first example, y equals 2x minus 5. So we're given a list of inputs. So if x equals negative 2, I would substitute negative 2 in for x into my equation. And then I would simplify it. What is 2 times negative 2? And negative 4 minus 5? Negative 9. So my output would be negative 9. And what would my ordered pair be? So then if I have an input of negative 1, 2 times negative 1, and negative 2 minus 5? So my output is negative 7. What's my ordered pair? Okay. Finish the table of values for the next 3. An input of 0 would give me an output of what?
Negative 5.
Negative 5. So I get 0 and negative 5 for my ordered pair. What about an input of 2? Negative 3. And an input of 2?
Negative 1.
So now if I go to graph these points, I have negative 2 and negative 9, negative 1 and negative 7, 0 and negative 5, 1 and negative 3, and 2 and negative 1. Okay? Can I join these points? Yeah. Is it possible to have an x value between 0 and 1? Yes, I could. Because I'm not given a context. So if I'm not given a scenario to use this equation, I could use any possible x value. So I would use a ruler so that I could draw a straight line, and I would join these points. And we're asked to extend the line in both directions with arrows at both ends. So then if I put arrows at both ends, that's what my line would look like. So then the question says, use the graph to determine the value of y when x is equal to 6. So if I look at x is equal to 6, I go up to the line. This would be my point. What's the y value at that point? 7. So it says use the equation to determine the value of y when x is equal to 7. So my equation was y equals 2x minus 5. When x equals 6, I have 2 times 6, which is, and 12 minus 5 is 7. So we have verified the answer. So then part F says write the value of y when x equals 6 into the table of values. So that's right here. And then G says use the graph to determine the value of x when y is equal to 3. So when y is equal to 3 would be, this is when y is equal to 3. So I follow it along to the graph, follow it down, or sorry, that's not when y equals 3, when y equals 2. There we go. So what's the value of x when y equals 3? 4. So I can put this into my graph. X equals 4, y equals 3. What kind of graph do we call this? A graph? What can you tell me about the line? What kind of line? Pardon? It's linear. It's a straight line. And the word linear has line written in it, has a hint. Okay, so let's look at the next equation. Consider the relation described by the equation y equals x squared minus 6. So we're going to do the same thing that we did before. Inputs and outputs. So this time if I have an input of 4, y equals 4 squared, which is what?
16.
And what's 16 minus 6? So my output would be 10, so my ordered pair would be 4 and 10. So now I want you to finish the table of values.
Looking at the front differently. Side.
If I have an input of 9, or sorry, not input of 9, input of 3, what would my output be? 3, because I'd have 9 minus 6. So my ordered pair, 3 and 3. Input of 2, negative 2, 4 minus 6. Input of 1, negative 5, because I'd have 1 minus 6. Input of 0, negative 6. Input of negative 1 would be negative 5, because negative 1 squared would be positive 1. Okay? Be very careful when you put negative 1 squared into your calculator. That negative is attached to the 1, so on your calculator you need to attach them together. You need to use brackets. Because if you don't, the calculator for negative 1 squared will give you positive 1. If you go like this, the calculator will give you a negative 1. Because the calculator will do order of operations, and it looks at this minus sign as being a multiplication. So it squares the 1 and then puts the negative. So I need to use the brackets there. When x is equal to negative 2, what's my output?
Negative 2.
And negative 3, the output would be? So I get negative 2 and negative 2, and negative 3 and 3. So let's plot these points. I've got 4 and 10, 3 and 3, 2 and negative 2, 1 and negative 5, 0 and negative 6, negative 1 and negative 5, negative 2 and negative 2, and negative 3 and positive 3. So then question C says use the symmetry of the graph or the table to predict what the value of y is when x is equal to negative 4. So when x is equal to negative 4, what would y be equal to?
10.
And using the symmetry of the graph means if I look at what positive 4 equal, I get this 10. Because this line here acts as a mirrored line. So then question D says use the equation to determine the value of y when x equals negative c to verify what you did, or sorry, when x equals negative 4, to verify what you did in part C. So in my equation, y equals negative x squared minus 6. So negative 4 squared equals 16, and 16 minus 6 would give me my 10. And then it says write the value of y when x equals negative 4 into the table of values using this blank space. So when x equals negative 4, y equals positive 10. Then in part F, it says connect the points on the grid with a smooth curve. Okay? So a smooth curve means you're going to make this. What shape am I drawing? A U shape. As best as I can going through the points. We call this type of a non-linear relation? Why do we use the word non-linear?
Because it's not a line.
It's not straight.
It's not a straight line. It's still a line, it's just a line that curves. So we call this a non-linear because it is not a straight line. Now here's a quick question for you before I give you the next questions. The equation for this graph was y equaled x squared minus 16. Minus 6, sorry. For that other equation, the one with the speed and the cost was equal to 0.001. Where did that question go? 0.01 s, or 001 s squared minus 0.14 s plus 12.4. And both of these graphs gave me this U shape. What do their equations have in common? I have a variable squared. This is called a quadratic. You don't need to know that name. You just at this point need to know it's nonlinear. But we look at these next year. We look at quadratic equations in Math 20. In both Dash 1 and in Dash 2. So the questions that I want you to work on is question number 5 and 7, 8, and 9.